Okay, thank you for inviting me here. Just full screen, just a second, yes. This is the title of my talk. It's devoted to a well-known problem in optimization. One of the key problems, one can say, devoted to overcoming local optima. It will be a survey which is biased somehow, because the theme is very broad, and there are many views on this, many ways to overcome this problem. But I will describe how I view it myself. Here is a couple of figures. One of them we have seen today already, and they demonstrate how versatile may be the landscapes with the local optima. And we always want to find the global one. And we can see that the landscapes can have a lot of local optima. And this is one of the parameters, how many of them. Another parameter is how deep they are, etc. And so one of the ways to overcome, yes, in discrete optimization, of course, it is not so easy to draw the landscape, because usually we have multidimensional problems with hundreds of thousands of variables, and discrete like 0, 1 to the power of n search space. And we want to maximize, for example, just to be specific, we want to maximize some fitness function or objective function. Again, we have some kind of neighborhood for any point y. We can say that there's a set of neighbors n of y, which is a subset of feasible solutions, of the set of feasible solutions. The local search starts from some initial solution y0, and moves to some improving solution within the neighborhood, and continues until there is no improving move in the neighborhood. So that's what we call by a local optimum. And once we have reached it by the local search, we have to make some hard decision whether to start from scratch, from some random point, or climb against the gradient, or do some other tricks. And so one of the popular approaches is the evolutionary algorithms, which are not so greedy, not so locally oriented as the local search. And here is one of the well-known outlines, well-known schemes of the genetic algorithms, which dates back to the works of Holland and Goldberg. We can call it a non-elitist genetic algorithm. So we have a randomly initiated population P0, and until some termination condition is met, we perform these steps. We select parent individuals using some selection operator, which randomly chooses the individuals from the current population, giving more chances for those who are more fit. Then we apply crossover, mutation, and basically we don't assume some elitism. So we don't copy the best solutions from the current population. We just produce the whole new population using selection, crossover, and mutation. Here we can see some basic examples of selection. For example, mu, lambda selection chooses uniformly at random among the mu best individuals in the current population. Bitwise mutation changes each bit with a given mutation probability Pm in the binomial distribution fashion, like Bernoulli scheme. Uniform crossover takes each bit independently, either from parent 1 or parent 2, This is just one of the examples. And another approach is based on elitism. Here's an example of elitist genetic algorithm, mu+1 genetic algorithm. I will not go through all the steps because they're very similar to the previous algorithm, but unlike the previous GA, here we produce just one offspring and add it into the population in the place of the least fit individual, or on a random position in the population, but random among the worst half of the population, for example. And there's a long controversy in the area of evolutionary computation about the role of elitism. Is it good or is it bad? Of course, elitism is good because we keep the best found solutions, and we can quickly find improving moves. But then once we have found local optimum and many copies of it in the current population, it is hard to improve it and go beyond that area. So let's look at the crossover first of all. Does it help to overcome local optima? One of the well-known examples in the theory of evolutionary algorithms is called jump function. Here we have a formal definition of it, and it is for 0-1 binary strings, and length of the string is n, and it is defined in terms of L1 norm. So we count how many 1 bits are there in the bit string. If we have less than n minus r bits, r is a parameter of our objective function. If it is less or equal to n minus r, then we have a linear function. The more bits, the better. The more 1 bits, the better. But once we have reached this local optimum, actually a plateau of local optima, it is much more difficult to improve, because then the fitness decreases as we increase the number of ones in the string. But the global optimum is the string of all ones. This is the global optimum. What can we see for this function? One of the first examples, one of the first results are proved for the elitist 1+1 evolutionary algorithm, which is the most simple algorithm we can imagine. It was suggested many times independently. For example, Leonard Rastrigin called it локальный поиск с адаптацией, локальный поиск с пересчетом при неудачном шаге. It's difficult to translate in English, but the idea is that we produce an offspring by mutation. If it is better than the current individual, then we substitute the current individual by the new vector. Otherwise, we stay there. Jensen and Wegener proved that this algorithm with mutation probability 1/n on jump function has an order of n to the power r time complexity. Formally, it is called expected optimization time. So it is the number of queries to the oracle, which gives us the fitness function. So it's n to the power r, and if we look at more recent results, we will find that including the crossover into the algorithmic scheme, for example, mu+1 GA, improves the runtime by an order an order 1. So we have n to the power r minus 1 times logarithm. And in experiments, we also can see that if we switch off crossover in mu+1 GA, this is the blue graph here, the runtime increases. So even if we have a population of mu individuals it doesn't really help. We need crossover to overcome this local optimum. And it is very interesting how it can overcome that local optimum. It is necessary to have a sufficiently diverse population so that we can combine two opposite individuals which like complementing each other, where one has 0, the other has 1. And then we have good chances to obtain the global optimum from those two local optima. And we compare these experimental results to the we compare this to the experimental results on a real life problem called buffer allocation problem. It is assuming we have a production line which has machines which are subject to failure, and they have a failure rate lambda I for each machine mi, and then they can be repaired, and the repair rate is mu I for each machine. And then to produce a part, it takes ui time units on average for each of the machines. So if machines break down, then the parts arriving to those machines get accumulated in the buffers. For example, in front of machine M4, we have buffer B3, and until it gets fixed, we have to accumulate them in the buffer. If it is overflowing, then the previous machine gets blocked. And so it's decreasing the production of the whole line. The larger buffers we have, the greater average production rate will be. So if we increase the buffers, it is better, but then we have to pay more for that. And also we have more parts in store in each of the buffers, which is also inventory cost, which is not good for us. This problem has been investigated for many years. For example, Boris Alexandrovich Sevastyanov proved that there's a steady state distribution for the average number of parts in this for this Markov chain, which describes this system, and we can calculate the average number of parts per unit of time. And there are many models for it which allow us to compute it exactly or approximately. And one of the approaches is to reduce the whole series parallel line to a single machine which is equivalent to the whole line, and then we can evaluate this machine and say how efficient it is. And in the optimization criterion, we can combine revenue for the production of parts with the cost of buffers configuration, with the average steady state inventory, and optimize this. So we have several problems from some of them originating from the real life instances in Renault car production. Two of them are displayed here, sorry. And some of them are made up, some are borrowed from other authors. And we can consider the landscapes of the objective function of this problem. If we run the local search for a multiple number of times, we can plot each local optimum as a dot on this graph, where horizontally we have the distance from the best known solution, D, and vertically we have the fitness of the solution. And quite naturally, the further we go from the global optimum, the worse fitness we get. This is natural. This is called the big valley conjecture or massive central conjecture for the maximization problems. And some instances of this problem display a clustering phenomena, we see that the local optima gather up in clusters on the fitness distance diagram. And for this small problem, we see that clusters are quite clearly present also. BN5 it consists of just 5 buffers. AS6 has a larger number of buffers, but both of them have this phenomenon. And so if we think how the local search would work here, it would quickly find some cluster of local optima, but then it would be very difficult to move to the global optimum because it is far away from this cluster of local optima. So what can be the reasons for such clustering effects? Well, in this specific problem, there are 3 reasons, basically. One of them is the symmetry of the search space. If we have, for example, it's known since 1969, if you have a line which has identical machines and identical buffers in it, then swapping, not necessarily identical, just 2 machine line. If we swap the first and the second machines in it, we will have the same fitness function, the same production rate. And so the landscape of of the fitness would look like this. We have 2 local optima here, for example, H1, H2, and symmetrically we have H3 and H4. And this can be one of the causes for the local optima to appear. And there are some other, due to serious parallel structure of lines and due to approximate nature of our computations. But anyway, we have this local optima which cluster. And if we run the genetic algorithm, we will see that the population gets concentrated on one cluster, then we get one individual in the other cluster, and gradually the whole population moves into that new cluster. So this structure is important for performance of genetic algorithms. And if we switch on and off the crossover, we can see that it is significantly changing the performance of the genetic algorithm. Here we can see 3 problem instances and 3 different crossover probabilities: 0, 1/2, and 1. So the higher the crossover probability, the greater average fitness we get after a run for 3 million iterations. And a similar phenomenon was also observed for the traveling salesman problem by Heinz, Whitley, and Hove. So we can conclude that for the crossover-based GAs, in the theory, it was proved that crossover can improve the GI performance, combining useful traits of different local optima from one cluster and thus jump into the other cluster or the global optimum. And we conjecture that the GA behavior, which we observed in the buffer allocation and which other authors observed for the TSP, are also due to the same role of crossover. So if we forget about crossover, would it be some help from the population to overcome the local optimum? There's a number of results in this area in theory of genetic algorithms, of evolutionary algorithms without crossover, which were obtained by Per Christian Lehr and Duquan Dang and myself. Here we have to look at the landscape structure in terms of density and sparsity of the local optima and the improving area of the landscape. So first of all, we can say that the hemisphere is the set of neighbors around our point X, which have a having a distance equal to R. Of course, there will be this number of neighbors for any point in the binary cube. And we will say that we have alpha dense set A with respect to some superset D if the fraction of neighbors within Hamming distance 1 around our point X is at least alpha for any point X in the set A. So here we have point X, we draw a radius equal to 1, and, oh, sorry, here we have a radius equal to 1 around our point, and we have at least alpha times n neighbors around in the set D, which we call superset, where we want to jump actually. And the sparsity is defined as follows. If we have a subset B, we call it epsilon sparse. If for any radius r, the fraction of the points inside the set B is not too high, it is less than epsilon times the number of elements in this hemisphere. So it is at most, the fraction is at most epsilon in the neighborhood of radius r. And there is one more technical assumption which we may not discuss right now. And so usually it is easy to optimize the functions which can be structured like layers, like levels. First level consists of individuals with the worst fitness. Then we flip one bit or constant number of bits. We climb into the next level, which consists of better individuals, etc. Then it is easy to prove that such algorithms perform well, and we can expect it that evolution will be successful here. But we can have deceptive cases. For example, here we have level I and level J. In level I, we have a solution X, which is better than the solution Y in level J, although level J is higher than I. So that's a deceptive pair of levels in our terminology. And we will say that we have a sparse local opt class if we have a family of functions such that we can split any problem instance into such layers, and each layer will be not far from the next layer. And the highest level AM will consist of the global optima only. We will have some, of course, we allow some deceptive pairs, but the deceptive areas should be epsilon sparse. And at the same time, the areas above the deceptive levels should be alpha dense. For example, in this figure, we can see a sparse red level, and we see orange level, which is dense, so to say. And we would like to see such a phenomenon where we can easily reach the orange area and then gradually reach the global optimum in it. So that would be good, but still we have deceptive areas in our case. Well-known examples, for example, one max function belongs to sparse local opt with parameters alpha equal to 1 and epsilon equal to 0. So it is a simple function. And the needle function is also well known, which is the opposite. It has very small density and very high epsilon sparsity. So there is a number of results which are obtained since the year 2021 here. First of all, shows that it is shown that evolutionary algorithms with elite individuals have exponential worst expected time on sparse local opt class. Secondly, the non-elitist evolutionary algorithms with appropriately chosen mutation and tournament size would have polynomial runtime for many alpha and epsilon parameters. The class sparse local opt is hard for all black box optimization algorithms if sparsity epsilon is larger than the density of the valleys, like we have seen in the needle example. And there are some examples of vertex cover or independent set problem where the non-elitist algorithms provably outperform elitist algorithms. For example, elitist 1+1 EA. So we can see that indeed population, especially non-elitist population management, allows to overcome local optima in some cases. And is it just a theoretical result, or is there some practical use of it? We can consider a family of well-known set cover problems. What is it about? Suppose we have n subsets of a ground set U. The size of and we want to find a collection of such sets Si, so that it covers the whole ground set U, and the size of this collection is minimized. We can represent easily the solutions like 0, 1 bits and have penalty for violation of the constraint that we want to cover the whole U, and apply the genetic algorithms to this problem or evolutionary algorithms without crossover. So we considered several combinatorial optimization problems from a well-known OR library based on Erdős problems or Stein set of problems. And we compared elitist 1+1 EA, 100 plus 200 EA, and non-elitist algorithms. We gave the same number of fitness evaluations for each of the algorithms and repeated the experiments for 40 replications. What we see here is the frequency of finding the optimum for different mutation rates, because all these algorithms, the efficiency depends on mutation, the proper choice of mutation. And we can see that the 2-tournament EA or 3-tournament EA perform much better if we have right choice of mutation compared to the 1+1 EA, which is in purple here. And the tournament selection is used in non-elitist population here. And for other problems of this of different nature, we in the set covering problem, we can see again. We can see the same behavior. So we can conclude that local optima in clusters may be combined into better solutions using crossover. The theory is supported by experiments with buffer allocation problems and the TSP. The elitist evolutionary algorithms fail on problems with deceptive local optima. Non-elitist evolutionary algorithms can overcome the local optima surrounded by sparse deceptive regions and dense valleys. And theory is supported by experiments with the set cover problems. We have a number of open problems here. First of all, we can see that the theoretical results are mainly for some very abstract formulations and toy problems, and it is not clear how to apply this theory to practice. So there's a big gap between theory and practice. Also, the theoretical results are obtained for 0, 1 to the power n search space. But what about the integer search spaces, the sets of permutations, or real valued spaces? It is still open area for research. And also we can see that there are a number of parameters or features of a given instance which we need to evaluate in order to apply evolutionary algorithms, and two of them are sparsity and density, and also the number of local optima, distance from the local optima to the global optimum, etc. So in order to forecast these parameters, we need to develop fast algorithms which can evaluate them. So this is all. Thank you for your attention.
Thank you very much for your presentation. Dear colleagues, it's time to ask questions. You are welcome.
Thank you for your presentation. I have two questions. The first one, you have mentioned so-called deceptive problems. In many cases, local optima you can escape local optima just by inversion of your bit strings. So if we assume that some function have such attraction, deceptive attraction, we just can use special case of mutation. For example, with very low probability, but sometimes we can inverse our solution. If we are in a local optima, after inversion, we will be in a global optima. What do you think about such strategy?
Well, I think this is a very drastic approach to restart or to moving away from the local optimum. Sometimes it can be successful, but usually I think it is for the made-up problems. For the real-life problem, I think this is very unlikely to happen.
Okay, that's why we just can believe it can be helpful. That's why we can use such mutation with very, very low probability. Okay, thank you. And the second question, when we deal with the real world problems, how we can distinguish local from global optima? We just inside some optima. Actually, sometimes we don't know if we are in optima because we can be on some path to optima. So how to distinguish local and optimal for a black box optimization, for example?
Yes, it is an open area of research, of course. On one hand, we can observe our history of the search, and we can say, okay, for a long time we have no improvement, and so we have very low chance to improve further. But this is not reliable. This is not a reliable approach. Another approach, of course, if we have a gray box, if we have some additional knowledge about the problem, maybe we can obtain some upper bound for the global optimum. For example, using mixed integer programming or some other tools. And then we can have a good reason to stop in the global optimum because we have a proof that it is a global optimum.
I see.
Maybe some other ideas, but I don't know.
Thank you.
Okay, dear colleagues, any other question? Okay, may I ask a question? In such a gray box in practice, where from can we get this knowledge and what kind of knowledge it could be?
In gray box optimization.
Yeah. Not black box, but a little bit gray.
Yes. Well, if we have, for example, mixed integer programming formulation, for example, I would say it is a gray box. Or if we have some symmetry of the problem which is known to us, it's not possible to prove that we have found the global optimum this way, but still it can be helpful if we know about symmetries. For example, in crossover, we can avoid some unnecessary moves due to symmetries. For example, in the mutation, we can be sure that this area is not promising because we have visited the same area, but symmetric, in the symmetric part of the search space. In the optimization, in the crossover operators, we can formulate a optimal crossover problem, which says, given two parent individuals, what is the best possible offspring for these two parents? In the gray box scenario, we can solve this problem rather efficiently sometimes. And then it is a very helpful addition to the algorithm.
Well, I do not know this English word, but it seems to be играть под давки. Nature will never играть под давки с нами. And second question, how do you think whether application of self-configuration in evolutionary algorithm can help avoid this problem of preliminary convergence to local optima?
Yes, I think it is possible. Actually, we have one of the papers which is about the restarting rule for evolutionary algorithms, which tries to estimate how likely it is that we will have improving move in our current population, or we need to restart. It's based on maximum likelihood estimates, and so it's, in a sense, it is parameter tuning. And of course, there are many other approaches from machine learning to this. But all machine learning approaches, they are based on some assumptions, on some models, which are not perfect. Until we have found the global optimum, we don't know where it is. And we can be deceived by the history of search.
So configuring is not based on machine learning, just analysis of the result of the one population generation of algorithm.
Well, I would say it is still machine learning because we have observations, we learn on these observations, and we forecast most, well, for example, in the fashion of, how is it called? Обучение с подкреплением. Reinforcement learning way. I think it is a version of reinforcement learning. Maybe
Yeah,
I'm biased.
But it can help to avoid preliminary convergence.
It depends on what we call the preliminary convergence. I think preliminary convergence is when the population gets stuck in a set of local optima far from the global optima.
Not far, maybe in closest neighborhood, but not in global optima.
Yes, meaning that it is far in terms of objective function. It is something which makes us unhappy. If it is very close to the global optimum in terms of the fitness, then it is no big deal, right? But if it is far, then we are unhappy. And that's a preliminary convergence, which we want to fight. And in this case, if we just have observations of what we have seen before, how do we know if the global optimum is somewhere not found by us? I think it is possible to prove that this problem is NP hard or something like that.
Okay, I see. Thank you. Dear colleagues, who would like to ask a question? Okay, nobody. Thank you very much for your presentation. Thank you very much for answering our questions. And you are welcome for the next conference as well.
Thank you. Goodbye.
Okay. Goodbye.